Hello and welcome to Otten Math. In this edition of Otten Math, we're going to talk about solving quadratic functions by factoring. Okay, so let's step back a second and talk about definitions in terms of quadratics. So a monomial is an expression with one term. Mono is one. Nomial or name is term. Okay, so we have one term. An example would be x squared. Binomial is an expression with two terms. So in this case, we have bi, which means two names, two terms, x squared plus 2x. And a trinomial is an expression with three terms. So x squared plus 2x plus 1 would be a trinomial. And the quadratic functions are typically going to come in expressions with three terms. X squared plus 2x plus 1 would be an example of a trinomial quadratic. Okay. So let's talk also about factoring special products. Now there are special product patterns, and I'm going to give you three of them. One is the difference of two squares. So a squared minus b squared, and that results in a plus b times a minus b. Now you can go through your normal factoring routine to get a plus b times a minus b, but it helps to see a special factoring pattern and to be able to factor that pretty quickly. So if I had something like 4x squared minus 9, I can take a look at that and see that I have two perfect squares and 4x and 9. And then I can rewrite this as 2x plus 3 times 2x minus 3 real quickly without going into the process of factoring in my head or factoring through the diamond and box process. So just remember these special product patterns. If you see perfect squares in the first and second term, you have a minus sign here, and you only have two terms, 4x squared minus 9, without an x, you might want to think that this could be the difference of two squares, so the difference of a squared minus b squared. We also have perfect square trinomials, and perfect square trinomials, an example would be a plus b squared, and that results in a squared plus 2ab plus b squared. An example would be x plus 3 squared. So x plus 3 squared, if I were to write that out and use my foiling method first, outside, inside, last, I'd get x squared plus 3x plus 3x plus 9, which is equal to x squared plus 6x plus 9. So again, if you see a perfect square here at the in the c value, then you can think, is this a perfect square trinomial? So that's a perfect square trinomial when I'm adding, when I have a value or root which ends up being negative, and when I'm adding the two values in the factor together, and then one in which I'm subtracting. So another case might be x minus 2 squared, so x minus 2 times x minus 2, and that's the same as x squared minus 2x using my foiling method, minus 2x plus 4, or x squared minus 4x plus 4. So again, the reason why we show you these special product patterns is because we want you to recognize these patterns when you're doing the factoring to help you simplify the process of factoring quickly. All right, now let's go into the lesson of solving quadratic functions by factoring. So we call solutions of a quadratic equation, we call those roots. And the roots are just locations where the parabola, the graph, crosses the x-axis. And we also need to know the zero product property, because the zero product property is going to help us find out the roots of the equation. The zero product property it just states that whenever you have something that's 0 and you multiply that by another value, then that result is going to be equal to 0. So 5 times 0 is 0, 6 times 0 is 0, 10 times 0 is 0, 0 times 10 is 0. So anything times 0 is going to be equal to 0. Now eventually what we want to do in finding the roots is we want to find that value for x when y is equal to 0. So at this point here, one of the roots, the value is going to be something for x but 0 for y. Here it's going to be something for x but 0 for y. So anything along the x-axis will have a result in a coordinate for y as equal to 0. And that's why we need the zero product property, because we're going to solve the equation and define y as 0, solve the equation of the quadratic when y is equal to 0. Okay, so solutions of a function represent the x-intercepts of the function, where the graph crosses the x-axis, is what I mentioned. And in the graph of, remember the intercept form, y is equal to a times x minus p times x minus q, the zeros are p and q. So if I were to write, here is my intercept form, it's a factored quadratic. So x minus 2 times x minus 6. So the graph of y is equal to a times x minus p times x minus q. The zeros are p and q, and in this case, my zeros are going to be 2 and 6. Okay, so why are they 2 and 6 and not negative 2 and 6? Well, we're trying to find the values of x that make this statement true, or this equation true. So we're trying to find the value of this term here that results in 0, remember in our zero product property, or the value of this term here that results in a 0. And the two possibilities are going to be 2, so when x is equal to 2, and when x is equal to 6, then either one of these values will end up being 0. And remember, the zero product property states that anything times 0 is 0. So I would have, in this case, if it were 2, I'd have 0 times negative 4, which would equal 0. And if it were 6, it would be 4 times 0. That would also equal 0. So my roots of the equation are 2, 6, and my x-intercepts are going to be 2, 0, and in this case, 6, 0. Okay, moving on. So let's talk about actual steps in the factoring process. All right. So when you factor, there are several steps to go through. The first one is to look for common factors. So in this example, I have 8m squared plus 56m minus 120, and I'm going to look for a common factor. So each of these coefficients is divisible by a certain value. Okay, the common factor in each term is going to be 8. The second thing you want to do is look for special product patterns. So we have the perfect square trinomials, the difference of two squares. You want to look for the a and b values that are perfect squares. Okay, so in this case, I don't see any perfect squares in the initially factored quadratic that I presented to you. So we're going to move on to step number 3. Okay, if there are special product patterns, you're going to simplify and repeat number 2. If there are no more embedded product patterns, which is the case, we're going to move on to step number 3. Now, I'm going to move on to a different example from the one that I previously gave you, just to make things simpler for us. And I'm going to change the example to x squared plus 6x plus 8. But you can also go back and try to factor m squared plus 7m minus 15. Okay, so I'm going to use a diamond and box to factor this quadratic, and you can also do this in your head, but the process that you go through is a similar process, either in your head or through the diamond and box process. Okay, so in the diamond and box process, we're going to put the c value on the top, and the b, remember b goes on the bottom, b for bottom, on the bottom of the diamond. So c is on the top, b is on the bottom. We're going to take the factors of c that add to b. Let's figure out the factors of 8 that add to 6. So I have 1 and 8. That's not going to work. So I have 1, 8. I have 2 and 4. 2 and 4 look like they're going to work. So I place 2 here and 4 here. And it doesn't matter if 4 is on the left and 2 is on the right. And I'm going to move on to continue the step. I have 4 and 2. Then I'm going to create my box. In the box, I'm going to put the first term of the quadratic, x squared, in the upper left-hand corner, and the c value on the bottom right-hand corner. Then I'm going to place some marks here, and I'm going to find the common factors of the columns and rows. So the common factor of the column is going to be x. Common factor of the second column is going to be 2. Common factor of the first row is going to be x. Common factor of the second row is going to be 4. So I end up with x plus 2 times x plus 4. That's my factored quadratic. Now, if I wanted to provide a solution for the quadratic, then I would have to find the values of x that make either this factor 0 or this factor 0. And that would be negative 2 and negative 4. So those, if I were to solve, it would be x is equal to negative 2 or negative 4. If I just wanted you to factor, you'd give me these two factors. Okay, so we've already gone through the process. Outside next to the box, place the common factors of the rows and columns directly above and to the left. I'm going to use the values created outside the box as my factored quadratic. The values on the left represent one factor, and the values on the top represent the other factor.